We typically group metallic elements by how they look and feel. In their pure state, they have a shining surface known as metallic luster. We can hammer them into thin sheets, a property called malleability, and stretch them out into wires, which is known as ductility. This diagram shows a classic way to test heat conductivity. We clamp an aluminium wire to a stand, attach a pin to the free end using wax, and heat the clamped end with a burner. As the heat travels down the wire, the wax melts and the pin drops, demonstrating that metals are excellent conductors. Metals are also sonorous, which means they produce a distinct ringing sound when struck against a hard surface. Because of these reliable physical traits, we use them for specific daily applications, from cooking vessels that need to rapidly conduct heat to school bells that need to project sound. But categorizing elements purely by their physical traits falls apart quickly. Take mercury. It is classified as a metal, but it exists as a liquid at room temperature. Or look at alkali metals like sodium. They are so soft you can cut them with a standard butter knife. The exceptions apply to nonmetals as well. Iodine is a nonmetal, yet it has a distinct metallic shine. Carbon, in the form of graphite, is entirely non-metallic, but it is an excellent conductor of electricity. Because these physical rules are riddled with contradictions, we cannot rely on appearance alone to group elements. To accurately classify them, we have to test how they chemically react with the world around them. Almost all metals combine with oxygen to form metal oxides, but they do so at vastly different speeds. Potassium and sodium catch fire immediately if exposed to open air. Silver and gold, conversely, ignore oxygen entirely, even at extreme temperatures. This diagram shows the chemical behavior of aluminum oxide. While most metal oxides are basic, aluminum oxide is amphoteric. This means it reacts with both an acid, hydrochloric acid, to form aluminum chloride, and a base, sodium hydroxide, to produce sodium aluminate. This schematic illustrates the water reactivity test, which reveals a broad spectrum of violence. Sodium explodes in cold water, but metals like iron or zinc ignore cold and hot water entirely. To force a reaction, steam must pass over a heated metal sample, stripping away oxygen to form a metal oxide and releasing hydrogen gas into the collection jar. Adding dilute acids to metals usually produces a salt and more hydrogen gas, yet noble metals resist even strong acids. Dissolving gold requires aqua regia, a highly corrosive fuming liquid made by mixing concentrated hydrochloric and nitric acids. This illustration compares two setups to determine chemical rank via displacement. On the left, an iron nail placed in copper sulfate kicks the copper out of the solution, proving iron is more active. On the right, copper fails to displace iron from iron sulfate. Compile all of these tests and you get the reactivity series. This chart lists metals in decreasing order of chemical activity. It places volatile potassium at the top, drops past iron and lead, crosses the hydrogen baseline, and bottoms out with highly stable gold. We can use this specific ranking to predict exactly how a metal will behave in a chemical reaction, but it only describes the hierarchy. It doesn't explain the underlying mechanics causing these drastic differences. To understand why sodium explodes while gold sits quietly, we have to look inside the atoms themselves. Chemical activity is entirely driven by an element's drive to achieve a completely filled outer electron shell, a stable state naturally found only in noble gases. This animated model shows a sodium atom. Metals are defined by having a surplus of 1, 2, or 3 electrons in their outermost shell. To achieve stability, that single outer electron is ejected. This leaves sodium with a perfectly full inner shell, converting it into a positively charged cation. Nonmetals are in the opposite situation. This chlorine atom has 7 electrons in its outer shell. It is missing exactly 1 electron to reach a stable octet, forcing it to act as a scavenger to complete its shell. This visual maps out the formation of sodium chloride. When these two elements meet, the surplus electron from sodium is transferred directly into the vacant slot in the chlorine atom. Because sodium lost an electron, it carries a positive charge. Because chlorine gained one, it becomes negative. These opposite charges attract, locking together through strong electrostatic forces to form a stable ionic compound. This diagram shows a slightly more complex trait. Magnesium has 2 extra electrons. To reach stability, it gives 1 electron to a chlorine atom and its second electron to another chlorine atom, forming magnesium chloride. Every physical trait we observe, The shine of a mirror, the ring of a school bell, or the sudden burst of hydrogen gas is a macroscopic symptom. It is the visible result of atoms trading electrons to secure subatomic stability.